Okay, so let's make a start. So last time we went around and we looked at all the lattice diagrams, okay, and how we could solve for transmission lines in the time domain. Okay, so we'll just quickly finish that off. First of all, by looking at a couple of special terminations. Okay, so we have one of those specials is the open circuit termination. Okay, so open circuit means that the load impedance goes to infinity, right? So what will be the reflection coefficient at an open circuit? Anyone? Sorry, 0? Okay, it will be it's going to be R minus Z naught and R plus Z naught. So if R is infinity, it will be 1. Okay, so it means that the forward wave, the backward wave is the same as the forward wave, right? At voltage, because they have to add together so that the current cancels out. Okay, because we know that I of the forward wave is V plus on or V1 on Z naught, and of the backward wave it's V2 on minus Z naught. Adding together they cancel out, right? So that's one thing to remember. Okay, so because current's got to be 0 at the end of the line. Okay, and so if you don't have this matched, then of course the source is not matched and you get multiple reflection. Okay, so the other special one is the short circuit termination. So here R is equal to 0, right? Okay, and in that case we see that we get a reflection coefficient of -1. Okay, so the reflected back wave has a voltage the minus of what the forward wave. Okay, so those two add up together to give the voltage at this point to be 0, right? Which is what is required of a short circuit. Okay, so they're just two special cases. Okay, so far we've just looked at resistive terminations. Okay, we can see that in the Laplace domain, it allows for complex reflection coefficient. Okay, because we could have a reactive load which is has some function of S in the Laplace domain. Okay, so it could involve inductors and capacitors. Okay, so we're going to go for an example with that and see how we can handle reactive loads, the end of the transmission line. Okay, so you can see that we can get a reflection coefficient which is not just a simple number, but a function of S. Okay, so we're going to do an example. The example will be when we've got a capacitor. Okay, so what's the impedance of a capacitor? Anyone? Yeah, 1 on CS, because we're in the Laplace domain. Okay, so 1 on CS. Okay, so let's go through and do that. Okay, so it is so we have V of S, and it's going to be a step function going from 0 to 2e. Okay, 0 to 2e minus V of S. So V of S of t equals 2e times ut, something like that. Okay, you see that? Yeah. Okay, then we've got it's a matched source in this case. Okay, it actually turns out a number of ways we could do this. Okay, 1 on C. Okay. And so this is at x equals x0 and it's x equals 0, right? Okay, so we could find, which is what we're going to do, find the reflection coefficient at this point and find what the forward and backward waves are, and eventually find I think we're looking for what's across the load and also what happens across the source. But is there some other way that we've already described where we could solve for this? This is Z naught. I think we went through this in the last lecture. Remember? I think last lecture or so we talked about matched source and loads. So what would we do? Well, it'd be actually the easy way to solve it. I'm not going to do it the easy way, but which would be the easier way to do it, considering that RS equals Z naught? Anyone? Sorry? No. I think remember a few lectures back, a lecture or so back, we said that if we looked in the Laplace domain, if the actual source is matched to the transmission line, then it's just the same as moving the source to the end and having a delay. Remember that one? Yeah. So we could do that, couldn't we? We could, remember we went back. Let's see where it was. It was somewhere here. Match source impedance, Laplace domain. Here we are. Okay, so it could be just effectively just a delay, right? And then that would be easy because it would just be u of t minus t, right, instead of u of t there, and then you could solve it with just KVL, right? Okay, but anyway, we won't do it like that. We'll look at using a complex reflection coefficient just to go through this and see that it may be that in some cases you may not have this matched, something like that, right? So and then you couldn't do that. It's in the course. Let's do it. Okay. I mean, if I was given this in an exam, that's what I'd do. I wouldn't go through the hard way. Okay. Let's do it. Okay. Did that. Here we are. Okay. So we know that rho S equals Z load S minus Z naught, which is just a number, so it's lossless. Z naught equals R naught, right? 1 Z load of S plus Z naught. So it's going to be 1 on CS minus Z naught on 1 on CS plus Z naught. We multiply top and bottom by CS. We'll get it's going to equal 1 minus Z naught CS on 1 plus Z naught CS. And if we say 1 on tau equals Z naught C. Okay, so it's a bit like a time constant. Okay, so Z naught's to be like a resistance. Okay? So let's see, that's going to be 1 on tau minus S on S plus 1 on tau. Okay, what I meant to have? Yeah, something like that. Okay, so we know that's what our reflection coefficient is. We know what are we going to launch. So we've got to find out what we launch here at the. So we need to find V1 or V plus. What will we launch onto the transmission line? Anyone? So before it's got to the end and come back, what are we going to launch? So what is V1 of 0T? What's that? That position x equals 0. What will the forward wave be? So we've got, this is source impedance Z0. We have a line impedance of Z0. So what's that going to be? Come on, guys. Sorry. Yeah, it'll be this divided by 2, right? Okay, so it's going to be EU to T, right? Okay. So V1 in the Laplace domain will be just E on S, right? So you've got your tables here. Where are they? Here. Okay, so you know that U of T is 1 on S, right? So you know your Laplace domain stuff. Okay, so and then if it goes down the line, we know that V1 at x naught T is going to be, and say this time here takes time T. Okay, time T to get down that's the delay. It's called T. Okay, so x naught is going to be U of T minus T, big capital T. Okay, and we know in the Laplace domain, we know when we've got a time delay, when we've got time delay, we multiply by e to the minus ts, right? Okay, so E on S times e to the minus ts. Okay, so that's what's going to hit the end there. Okay. So we need to find V2 of x naught comma S equals something. Okay, it's going to be rho S times V1 of x naught comma S, right? That's what it's going to be. We've already said that. Okay, so and we've got that. That's already here. So it's going to be E on S e to the minus ts 1 on tau minus S plus 1 on tau. Okay, and the total this VL of x naught comma S will equal V1 of x naught comma S plus V2 x naught comma S. Okay, because that's the definition of it all. Okay, so that would be this plus that. Okay. So we've got minus ts plus. So we've got to invert those into from the Laplace to time domain, right? Okay, so we can do that with lookup tables, but the one we've got to get here, we can see that there's two poles, so we've got to get partial fraction expansion for that. Okay, so we can invert this one easy. Okay, but we need to do a partial fraction expansion to invert this one. So we've got two poles, so we're going to say that we've got to get that into the form of A on S, because that's one of the poles, S equals 0, right? Plus B on S plus 1 on tau, because the other pole is at minus 1 on tau, right? Okay, so there's not many people did 3021 here. You did. Do you remember doing all this? Yeah, good. Okay, so we've got to find A and B. Remember, we do that by taking this function. So we're going to A equals for S, for just the pole equals S, we multiply, it cancels by the actual pole. Top line, S plus 1 on tau. And the value added at S equals 0, right? Because that's the first pole. So that's going to equal E times 1 on tau times divided by 1 on tau equals E, right? So that's what A is going to be. Okay, and B will be S plus 1 on tau times E on S, 1 on tau minus S plus 1 on tau, cancel. The value added at S equals minus 1 on tau. So that's going to be, is that right? Yep. Equals E on minus 1 on tau times 1 on tau plus 1 on tau, so 2 on tau. Okay, and the taus will cancel off, will they? Yep, they will. This one will go up to the top, that is at the bottom, equals minus 2e. Okay, so VL of x S equals E on S e minus ts plus E on S e to the minus ts, because I've still got that there. Okay, we know that's just shifting it in time. Okay, that's just shifting, giving a time delay when we come back. Multiplying anything by that, just making it a time delay. And we've got minus 2 E on S plus 1 on tau e to the minus ts. Okay, if we can see here that these E on S's are just step functions, and be 2 of them. Okay, and then this one we can see here, 1 on S plus alpha to the 1 is just going to be a decaying exponential. Okay, right. Okay, so we can see that it's going to be VL of x naught comma t equals 2e u to the t minus big T minus 2e u to the t minus big T. Remember that we're always talking about the one-sided, so everything's multiplied by this unit step function. Okay, and then we've got e to the alpha is minus t minus that on Tor, right? Okay, we could put that 2e minus 2e e to the t minus divided by Tor outside of u to the t minus t, okay? So that would look like, so at the end, you'd have, so VL would look something like, see if it's right, and you'd have nothing till you got to t, right? You wouldn't expect anything to arrive there before t, right? And then you'd have initially at t equals big T, it would still be 0, right? But then, you'd have this exponential decay of this negative term here, so it would eventually go up to that value. So it's a bit like a capacitor charging up, okay? So that would be the result, okay? So, yeah, that's the right thing. Is that clear how we did that? Okay, so that goes through it, what we get and all that stuff, okay? Okay, and what we get at the end. And coming back, you could also find what happens at the source, okay? Because, you know what you've launched. You've launched this initial step of 0 to e, okay, and then coming back at 2t, you would get this v2 x of s, but delayed by another 2t, okay, which would be what would it be? Well, it's going to be this, okay, it'd be that component, okay, that would be that part coming back. So you could see that at t equals and be delayed by 2t. So you'd get initially minus, it would be, you'd have this minus 2e this term, and you'd have just one of these two, okay, so this would be just e, so but delayed by 2t, and you can see that at 2t it would be, this would be 1, so you get minus e, so it goes straight down again, and then it would start charging up, right, okay, which is what you see here, okay, is that clear as mud? Yeah, everyone? Yeah, okay. So the thing is, you can see that initially the capacitor looks like a short circuit, right, because, you can't change the voltage across capacitor instantly, okay, so, it's like a short circuit, so V across the capacitor has to be 0, so it's going to take all that current that the line can supply, and it's going to try and maintain the potential difference between the top and bottom as 0. And then as it charges up, of course, it eventually becomes like an open circuit, right? Because in a long-term DC steady state, that if there's no voltages changing, then the current through the capacitor is 0, right? So it should be an open circuit, and that's what it looks like. In the end, it looks like an open circuit, right? True. We could look at an inductor, okay? I don't think we'll go right through this, but a similar procedure, okay? Now we've got the complex reflection coefficient being, I don't do that, I don't think, being this, okay? And we have this Tor is now ln Z0, okay? Okay, and we find a different waveform, okay, at the termination, okay? Go through all that procedure, and we can see that, the inductor, initially, you can't change the current through an inductor instantaneously, okay? Like the voltage on a capacitor, you can't change instantaneously. So initially, if there's no current flowing in the inductor, you can't instantaneously make current flow in it, so it must look like an open circuit, right? So for that instance that the wave arrives, it looks like an open circuit, okay? So you can see that it jumps up to 2e, which is what, if it was an open circuit, you get a reflection coefficient of 1, and you'd have the backward wave would be the same as forward, and you'd be up to 2e straight away. But then, the inductor starts conducting current, and then eventually it becomes, a short circuit, right? Okay, and you see that, there can be no voltage across the short circuit, so you eventually see no voltage there. Okay, so is any questions on, it's a bit more, so just allows, you can see that you can handle some more things with this. Okay, as I said, you could also, in this case, since the source was matched, you could also look at it from the point of view of just moving the load, the source to the end of the line. Okay, so it's just going to be a delayed version of what the voltage source is here. Okay, and it'd be a lot easier to solve. Okay, so that's sort of like most of the theory. So we're going to look at applying a lot of what we've learnt to a really quite useful situation. So now I brought one of these sort of boards in here as well. I didn't design this one, but I have designed a lot in a past life. So you can see you have all these integrated. So this is a high-speed system. I think the clock rates would be, so these sort of things were done in the late 90s, because I used to work at a company that did these. And the clock rates were hundreds of megahertz, and the rise and fall times of some of the signals might have been sub-nanosecond, right? So you've got reasonably high frequencies. You have similar frequencies nowadays on printed circuit boards as well. So you see you've got all these chips, okay, integrated circuits, and you have also these little packs here, okay? So these things are packs of resistors. You can see them here as well on this one, okay? So these are quite very fast integrated circuits, these ones here. These ones are just driving transmission lines, because this goes onto a backplane, and thing plugs in like this and transports data between different modules. That's what it does. And you can see here you have all these resistor packs. Okay, and each resistor pack you can see has 4 little separate resistors. Okay, and they're used to ensure that the signals transmitted from either one chip to another another or across the backplane to another board have certain qualities, okay, have integrity, okay, so that, and we're talking about digital signals here, right, so that going from 1 to 0, okay, but it's important that, the transition from the 1 to 0 or 0 to 1 is clean, okay, it's monotonically increasing or decreasing, okay, and it doesn't have any significant overshoots and doesn't have any extra incurred delay, okay, than what you'd expect, okay, and that's why we need to look at the transmission line properties, okay, the properties of the transmission line, and think of methods how we can achieve those required goals, okay. So, and the way we do it, you'll see soon, that is to put resistors into the transmission lines, okay, or just at the output generally of the driving circuits, okay. So some of the chips here, this one here, we don't have one. Oh, we do here. So you can see this one doesn't have very many resistor packs around it at all, okay, same. And that's because as circuits get faster, the manufacturers realize that these things become a problem, and this one happens to be a programmable logic device, so you can change the logic functions that it has inside of it, and some of the options you can choose for each of the input-output pins is whether it has a resistor already in series inside the actual driver of the integrated circuit, or it may, instead of having a very fast transition from 0 to 1 or 1 to 0, it ensures that the transitions are very slow, okay, so that the actual frequencies of interest are not the wavelengths of the frequencies of interest are not small compared to the size of the circuit anymore, so you can just treat it as a simple bit of wire instead of a transmission line, okay, so that's why there's less around this one, okay. And you can see here, so here's a classic example of just driving. So we've got there's probably someone here as well, but I can't see them quite as clearly. There's some here where you've got these long lines, so you can see here, this is the transmission line here going to some destination, and then we can see that we've got a resistor, okay. And remember, that line is on top of a ground plane, and the other input, so you remember we're talking about 2 ports, transmission lines, 2 ports, so the other input is actually on the ground plane, so it's located close by, okay. So the 2 ports to this line are just here, and then it can drive a signal all the way over to, it looks like somewhere over here, okay. So the idea of this part of this next lecture or so is develop a methodology to guide us in the design of print circuit board interconnects based on analytical models and also some simulation to verify it, and a consideration of a small number of practically useful topologies, okay. So we can have, we can group print circuit board interconnects into a number of classes. We can go point to point, right? So we go from, one driver to one receiver through transmission line. We could do point to multi-point, where we have one driver that drives a signal to lots of receivers, okay. And then we could have multi-point to multi-point, where there might be multiple drivers that drive to multiple destinations, okay. So we're not going to consider that because it's too hard, right? But these things, we can do stuff to actually make these things work, okay. So we need a model for the driver, okay. So to do this, we need mathematical models for all components in the system. So we have a driver, we have a transmission line, and we have a receiver. So for the driver, you'll see that we model it as an ideal source with perhaps some series resistance in it, right? There's some resistance, because that's not a bad model for a driver, right? And then transmission line, we've got the mathematical model for that. We assume lossless transmission line, and then need a model for the receiver. So what does the equivalent circuit for a receiver look like? And we're actually going to model them with a capacitance. So why would you expect that we model the receiver with a capacitance in this case? Anyone? Sorry. Yeah, that's true. But why is the model for these? So these are integrated circuits, and they're made with CMOS technology mostly nowadays, right? Most of these ones on here are CMOS. So why would the model for that, good model for that, be a capacitor? Anyone? Yeah, it's because so CMOS uses field effect transistors, okay, and a CMOS gate might look like a field effect transistor. You might have I think a P for inverter might look something like this, and an N transistor, and then that's the input, okay. And this might be plus 5 volts, 0, right? And this is the input's been driven here, and this is the output, okay. So this input, obviously at the edge of the chip where the signal's coming from outside, it's a lot more complex than this, right? But you can see it's basically dominated by these FETs, which look like capacitors, right? Okay, so they have an input capacitance. Okay, the current going in here in the DC sense will be 0, hopefully, or close to it. Of course, FETs don't have very little. The metal oxide semiconductor FETs, okay, have very little input current. Okay, because it's essentially just a plate that's on top of an insulator. Okay. So, the most appropriate model is a capacitor, okay? So, because that's what the inputs look like, okay? So, and it can be quite significant, the input, you'll get a data sheet, and it'll actually specify the equivalent capacitance of the input of the chip. It might be a few to tens of picofarads, okay? So quite significant, okay? Depending on how they design the chip inputs, okay? No, well, but not really. We're not interested in what happens here, right? We just want to see, So we just want to get something that models the I and the V here. That gives some representation. So we don't care what the chip uses it for. Our job is to take, from the transmitting chip, might have a chip here, it's got little signals and it's got ground. Okay, so all these things are, this is the ground plane or something, and then it's going to drive, say, a waveform, to some other chip that's on the other side, and that's also ground, and that's the TX line, transmission line. We want to make sure that what arrives here at this input also looks, something like that, and doesn't look like something like this. Okay, that's our job. We don't care what's happening inside the chip. We just want to model for what the VI relationships at the input to that chip is. A rough one. It doesn't have to be perfect. Just capturing the key characteristic. Okay. In this case, because it's CMOS, the key characteristic is that it looks a bit like a capacitor. Okay. And something of the order of 10 picofarad, something like that. Okay. That's what we're trying to just capture, the key characteristic of the VI relationship. Okay. So once we know a reasonable model for the VI relationships at the end of that the signal will see at the end of the transmission line, then we can abstract that whole concept of the system to just a voltage source, a resistance for some value, and this is some step function, it's ideal source, and then we've got a capacitor, right? And we want to find out what VL is going to be, okay? And that serves. So it's a good example as well. It serves. You can see how we need to make a model for this. We need to make a model for that, and they've got to be simple so that we can just capture the key characteristic. Okay? So it's just, I suppose, what we're talking about at the beginning of the course. Okay. So let's look at. We've got to try and get some structures. Okay. So first of all, we'll do point to multi-point, right? Okay. So we've got one source device here, and it could be driving. Let's go for a couple more minutes, and we'll call it quits. It could be driving a number of devices in like a star configuration. Okay, so they're all coming out from the one driver, or it could be driving it over a line that has then coming off at regular intervals. Okay, so uniformly loaded line, that's one we're going to look at. Okay, or it could be that it drives a line for a certain distance and then it drives a whole lot of receivers that are uniformly spaced. Okay, so we will look at this one. Okay, it should be the first one we look at is this one. Okay, we'll come back to perhaps one later. Okay, if it's not structured, okay, then it makes it difficult. Okay, so we won't consider that. Okay, so it's too complex. Okay, so you should avoid, if you're designing stuff, and if you do become an electronic engineer and design equipment, you'll need, and it's fast stuff, then you'll need to take these things into consideration. Okay, so you should keep this in mind. Okay, you shouldn't do things like this because you don't have any theoretical background to understand what's going to happen. Okay, and bad things could happen, and you don't want that to happen. Especially if you go through the whole process of designing a board, it costs a lot of money, takes a lot of time, comes back, doesn't work the way you want. We could also look at, again, there's star wiring configurations where we could have little clumps coming from particular devices, okay, with perhaps loads clustered close together. These are close. Now that's something we can handle eventually, okay, we'll talk about that. And eventually we'll see that the way to handle that is to consider it as a number of point-to-point actual systems, okay, point-to-point, so each of these will have a very strong driver, and we'll eventually see the best way to handle that is to have coming out where each of these lines are separated by a resistor and then functions as a number of multiple point-to-point type things. Okay. Non-uniformly loaded line, it's also difficult to handle. Okay, because we can't say anything about the characteristics of the transmission line. Okay, because these receivers effectively have a capacitance on them. Okay, so as the signal is going along, it will see different effective transmission line impedance. We know that transmission line impedance is affected by the capacitance per unit length. Okay, that's when we did the model, remember, of the small section. So these things will sort of add capacitance to that capacitance per unit length, and we could get reflections everywhere. Okay, so it's a bit tricky. This is one we will tackle first of, and here we could have an unloaded line, but then a uniformly loaded line. Okay. So what would be? Did anyone think how we could tackle this particular problem? How would you? Anyone got an idea how we could tackle this analytically? So we're adding along this line, very close together, little bits of capacitance. So what would you, knowing how we model the transmission line, do anyone think about how we could tackle that problem? Anyone? Okay. So we make some assumptions anyway to get it to where we can model it. We'll just quickly look at this very, very quickly, and we'll come back to it. We have to assume that receivers is distributed uniformly over the line. We model them as capacitor load, which we've already said. The receivers have equal capacitance, and they're close together, reasonably close together. Okay. So under those conditions, remember how we model the line. We can consider this uniformly loaded line to be a new lossless transmission line with different parameters. Okay.